Dear student, myself Dr. Surekha Jaiswal, Moreshwar College, Bhukardan, District Jalna. Today we will see Electrodynamics, course code number 302, semester 5. Now, today's topic is first unique theorem and second unique theorem. First unique theorem. Now, the problem of electrostatic primarily deals with calculation of electric field of given charge distribution. Generally, it is convenient to calculate the electric potential first and then the field can be calculated from the known value of potential by taking its gradient. Now, the proof of a proposed set of boundary conditions will be usually presented in the form of a uniqueness theorem. In the first uniqueness theorem state that the solution to Laplace equation in some volume V is uniquely determined if psi is specified on the boundary surface S. Now, proof of this first uniqueness theorem is: consider a volume V bounded by boundary surface S as shown in figure. See here, that is a boundary surface S. We want to determine value of the potential psi at a point in this volume V. At present, there is no charge enclosed by the volume, and thus Laplace equation can be used to determine psi. So, by Laplace equation, del square psi equal to 0. Suppose psi 1 and psi 2 are the two solutions of the Laplace equation. Hence, one can write del square psi 1 equal to 0 and del square psi 2 equal to 0. The meaning is both of these solutions assume the specified value on the surface S. The point is to prove that the two solutions must be equal. Psi 1 and psi 2 both are equal. To prove this, let us take difference, say psi 3 of these two solutions, that is psi 3 equal to psi 1 minus psi 2. That is the difference of two solutions, psi 1 and psi 2, that is denoted by here psi 3. Now, the difference will also obey the Laplace equation, and thus del square psi 3 equal to del square psi 1 minus del square psi 2, and that is equal to 0. And it take the 0 value on all boundaries since psi 1 and psi 2 are equal. But Laplace equation allowed two local maximum or minima or extreme occurs on the boundaries, so the maximum and minimum of psi 3 are both 0. Therefore, the psi 3 must be 0 everywhere, and hence psi 1 equal to psi 2. Now, if some charge is enclosed by the volume rho is the charge density, then using Poisson's equation we can write del square psi 1 equal to minus rho upon epsilon, and del square psi 2 equal to minus rho upon epsilon 0, so that del square psi 3 equal to del square psi 1 minus del square psi 2, and is equal to minus rho upon epsilon 0 plus minus rho upon epsilon 0, that is equal to 0. Once again, the difference psi 3 equal to psi 1 minus psi 2 satisfy the Laplace equation and has the value 0 on all boundaries. So, psi 3 equal to 0, and hence psi 1 equal to psi 2. Thus, the potential psi in volume V is uniquely determined if the charge density rho throughout the region, and second, the value of psi on the boundaries are specified. Now second uniqueness theorem. Consider a volume V surrounded by conductors. Let charge Q1 is put on first conductor, see in figure, that is charge Q1 on first conductor and charge Q2 on the second conductor, and so on. Now let rho be specified charge density in the region between the conductors, and uniqueness of value of field E is to be checked. When charges on various conductor surface are known instead of potential at the boundaries, then the second uniqueness theorem speaks about the uniqueness of electric field value in the region of interest. The second uniqueness theorem states that in a volume V surrounded by conductors and containing a specified charge density rho, the electric field is uniquely determined if the total charge on each conductor is given. Now see proof of this second theorem. Suppose there are two fields satisfying the conditions of the problem. Let both obey Gauss law in differential form in space between and the conductor, and thus we can write del dot E1 equal to rho upon epsilon 0 and del dot E2 equal to rho upon epsilon 0. By applying Gauss law in integral form, we get the Gaussian surface enclosing each conductor. We can write for each field as in closed integral over the surface first conducting surface E1 dot dA equal to Qi upon epsilon 0, and also closed integral over I conducting surface E2 dot dA equal to Qi upon epsilon 0. So similarly for the outer boundary, whether this is just inside on enclosing conductor or at infinity. Now closed integral over outer boundary E1 dot dA equal to Q total upon epsilon 0, and closed integral over outer boundary E2 dot dA equal to Q total upon epsilon 0. Similar to the proof of the first uniqueness theorem, we can take difference, that is here E3 equal to E1 minus E2. So obviously E3 in the region between the conductors will obey del dot E3 equal to del dot E1 minus del dot E2, that is equal to rho upon epsilon 0 minus rho upon epsilon 0 equal to 0. Further, over each boundary surface we have closed integral E3 dot dA equal to closed integral E1 dot dA minus closed integral E2 dot dA equal to Qi upon epsilon 0 minus Qi upon epsilon 0, that is equal to 0. Although the distribution of charge on each conductor is not known, it is sure that each conductor is equipotential, and hence potential psi 3 is constant, not necessarily same constant over each conducting surface. It need not be 0 for the potential psi 1, and psi 2 may not be equal. All we know for sure is that both are constant over any given conductor. Now let us take del dot psi 3 E3 equal to psi 3 into del dot E3 plus E3 dot del psi 3, and del dot psi 3 E3 equal to 0 plus E3 into minus E3 equal to minus E3 square. Now integrating the above equation over the entire region between the conductor and applying divergence theorem to the left side, we get volume closed integral over V del dot into psi 3 E3 into d tau equal to closed integral over surface S psi 3 E3 dot dA equal to closed integral over V E3 square d2. The surface integral covers all the boundaries of the region in question, the conductor and outer boundary. Now Q3 is constant over each surface if the outer boundary is infinity, psi 3 equal to 0, and there, so it can be taken outside of each integral. We get V3 closed integral over surface S E3 dot dA equal to 0, and thus minus closed integral over V E3 square d2 equal to 0. But the integrand is never negative. The only way the integral can vanish, that is E3 is 0 everywhere. Consequently, we can have E1 equal to E2. This proves that the second uniqueness theorem. Thank you.